Okay, now we want to start the simulation of the digital filter. This is only possible with the second tool, which I have called Windfc sharp. To run this, go to Toolprogramme, Toolprogramme Bayerline, and here you can find Windfc sharp. Modules. First, the solution Windfc sharp contains also the source code. If you only want to have a runtime version, here go to Windfc sharp run. Actual version here is 7.7.17. This is a folder which contains several DLLs, dynamic link libraries. To run the program, you need all the libraries offered in this zip file. So copy the zip file, unpack, and then start the executable file. Then you get the running second tool. We will start this soon, but before I want to start this, let's tell you something about this folder. Here I will store step by step all files I have created during this lecture. Here you see the simulation result, the text file of the step response, and here with the suffix WLN, this can be loaded with rec sharp. This contains a signal block diagram with all parameters. Okay, so far, after downloading the Windfc sharp tool, we can start the program, but before I have to tell you some main information about this tool. Yeah, first I want to explain what you can do with Windfc sharp. One main task is you can run a closed loop system. So a closed loop system, single loop system, has a controller and a process and a negative feedback and a desired value. And here you can see the result, and here you can see the controller output. Okay, how can you work with this program? You should know that the process can be selected by a menu point which is called ADC cards. Why is this called ADC cards? Because you can run real-time systems, and with ADC cards you select that card which is connected to your PC, and this ADC card then is connected to your process. So a process includes ADC and DAC card, and here you can select them. This of course needs hardware. In our lab we have different hardware and we can do this with different ADC cards, but of course for our lecture we can also select a hardware simulation, and then the computer works exactly like the hardware simulation. That means you can define a process and run the loop without connected hardware. But in the lab you will do this with real hardware. Okay, first we have to select the hardware. Next is the controller can be designed in a menu called controller design. This of course comes later, because today in this experiment we have a given controller, so we have just select the parameter of the PI and put in the Q1 and Q0. Then the whole loop, including setting of desired value, including selection which type of controller you want to have, in defining how many steps you want to see for the reference step response, and with which sampling time you want to see this, there is the main point in menu real-time controller, the real-time functions, real-time functions, and the top menu point then has to be selected, which is called adaptive advanced controller. Advanced controller. With this menu point, then you can select simple controllers, but of course all other up to adaptive versions we will discuss in this lecture. So with this big menu point with many settings and knobs and buttons and parameters, don't be confused with this window. I show you which settings you have to do to get a simple PI controller running with a simple process. Okay, let's start the program. If the program is opened, you see a menu line, some buttons. Here later this will be the area of the graphical displays and so on. Note it starts with English menu text. If you want to have German text for our German students, click on the German flag button, then all text information is in German. But of course for this lecture I will stay in English. Note that the ADC card for process and real-time functions for the loop is used today in this demonstration. So first I go to ADC cards. Here you see national instrument cards could be connected. German company Mailhaus card could be connected. Or here look, we have developed an I2C connection with USB port. So this is very cheap but really fast ADC connection to any other process. And here the third point is hardware simulation. If we open this point, you see a window where we can now select some prepared processes. You can type any digital filter. Today we want to go with the 2PT1 process. The K should be changed to a value of our given jetzt haben wir eine falsche Tastatur. Shit. Okay, now I have changed the keyboard and the number is 0.3175. We type it in 0.3175. The time constant for the first PT1 was 1 second, and the time constant for the second PT1 was 0.6 second. Then we go here to the delay, the sampling time. The sampling time should be milliseconds, 200 milliseconds. The rest, 2000. The rest should be unchanged. And we close the keyboard, and you see now here is a button because the hardware simulation runs with the internal digital filter. And the internal digital filter has to be prepared by this. FFZ is a transfer function of digital filter. Wait for chapter 7, then I will explain this in more detail. So if you changed here a number, click on this, and then you have the actual digital filter parameters for your hardware simulation. So the process is now prepared. We can close this window and start with simulation. Okay, for this I open the real-time functions menu point, and I have told you to select the adaptive advanced controller box. This is a box which is rather huge. You have many parameters to select, but I show you what today are important. First, the sampling time here. This is the sampling time box is already set to 200 milliseconds. in the hardware simulator and in the control box, the assembly time must be the same. We want to see 20 seconds. No, I think 50 times 200 milliseconds is the 10-second curve is okay. We select a PI controller. In the PI controller, and we select the unit step function. It's the input for the desired value. Yeah, these are the signal parameters for the desired value. We want to see a step function automatically stopping after 50 points. Unit amplitude is 1, no offset. And here is the area where we can type in the parameter of my PI controller. So this is the Q0 number, and we want to have 2.4. And here we have the Q1 value. We want to have a -2 input. So negative input number, -2. Na, hat's geklappt? No, 2 is missing. Wrong button, sorry. With a normal keyboard, this is much more easier than this with a touch pen. But try to do this with your normal computer. Okay, if I change numbers here, it is very important that you click on this button, because then these parameters are sent to the internal controller. So I click this and the rest should run. Now I have here some buttons. If I click on run, initial conditions are activated. In our case, the controller output here called XR, the controller output is 0, but you can do in lab experiment, we need some other initial conditions to prepare the process for the starting point. For example, a position control system can automatically be set to the starting point with this program. So I click on run, nothing happens, and now I can go to the button start reference step response. If I click on this point, then automatically the program runs. Here you see values changing, and this works in real time. The smallest time here is 1 millisecond, and if we have 50 points with 200 milliseconds, of course this takes 10 seconds. Now if we see for this curve, you see the final value will be 1. After 4 seconds we have reached the maximum point. This looks very similar to the curve we have already measured with my analog controller. We can also store this curve in a text file. I have prepared this. The name is reference step response PI controller with 2 PT1 process, digital controller with a Bayerline version. Store it, replace it. To compare our controllers, I of course want to show you what happens if I type in the Baumann parameters. Remember, the Baumann parameters are these parameters were in the integration. The last rectangle is ignored. Then the Q0 was 2, so I have to type in now different numbers with my crazy keyboard here, and the negative value then is negative 1.6. So look, Q0 is 2, Q1 is negative 1.6. That is the Baumann version. I send this controller values to the internal control program, and we can redo this curve. I delete the last curve. I want to see only one curve. The comparison I will do later in another window. I click on run. You see now the controller is controlled to 0. If I want to accelerate this process, I can push this button. This is only valid if I have selected the hardware simulator. Of course, in real processes there is no initial button. Okay, and if we click on start reference step response, you see the output is running up to the desired value 1, and this is the controller output value, and you see this curve looks very similar. The overshoot is a little bit higher. Let's store this curve also as a zim file, and then we can compare all curves now in the main window of my Windfc Sharp. I leave this window because now my simulation is completed, and in this window now I can load all 3 zim files so that we can compare the analog one with the both digital ones. The comparison can be done by loading these files. That was the analog curve. The loading window, I accept this. That is what we measure in Windfc. Now I open the Wireline version as a second curve, and I load the Baumann version as the third curve. And you see the differences are small. The red curve was my version, is a little bit faster, caused by using the newest value to control. The analog is in the middle, and the green curve was the Baumann version. It is a little bit slower with a larger overshoot. So you see the differences are really neglectable. Forget it. It is not important if you use the Wireline version or the Baumann version. The behavior in a closed loop system is nearly the same. So I close this demonstration, and we have finished now the PI section, and in the next video I want to add the differentiator, because we want, of course, see a digital PID controller designing and working. So wait for the next video.